Now, before we start, it would be a good idea for us to have some of these materials around for you so that it'll be easy for us to actually proceed. Definitely paper, notebook stuff that you can write down. And again, pencil and pen, calculator, periodic table. It's nice to have a phone. And what I'm also testing out to see is how this works in terms of polls and getting responses from you directly. So there is a website, pollev.com/Vinstan274. If you can log into that on Safari, Chrome. And there is also an app that you can install in your phones. It's also convenient to use if that's the case. It'll be good to have one of these ready when we are ready to use it and see if it's going to really work and help us in our learning process. So these are some of the things that you may want to have today for the rest of the classes as we go along. Now, I'm actually kind of proceeding from the point, thinking that some of the information that you already have based on the information that I collected is you already know about reversible reactions, law of mass action, homogeneous and heterogeneous equilibrium, how to write equilibrium constant expressions, and the relationship between Kc and Kp. So we will take up a few of the things that we need to learn. Let's see how it goes. The remaining part, what I plan to do is Le Chatelier's principle, talk about concentration quotient, look at the factors that affect equilibrium, and use that to predict the shift in equilibrium. And finally, ice-table problems if we have time. That's what we're really going to do today. Again, statement for Le Chatelier's principle is important, that you need to recognize it. You should be able to write in your own words. That's one thing that you need. Again, the statement goes, when a system in equilibrium is subjected to a stress, the system readjusts itself such that it negates the effect of the stress. Very simple, straightforward statement. Now, what we're going to look at is what factors affect equilibrium. We're going to look at the effect of concentration of both reactants and products, how volume change or pressure change affects an equilibrium, how temperature affects an equilibrium, how catalysts and inert gases may or may not affect the equilibrium shift. So those are some of the things that we are really going to look at. They also call that factors that affect equilibrium. So bear that in mind. So we're going to look at a reaction here for the reaction between nitrogen and hydrogen producing ammonia. So this is a homogeneous equilibrium. This is an exothermic reaction because heat is a product here. Now, if the system is in equilibrium, we are considering that the reactants are placed in a closed system. And if the system is in equilibrium, and if we add a reactant or a product, normally there will be a shift in equilibrium so as to consume the chemical that is added. So if you increase more reactants, what the reaction will try to do is consume it as quickly as possible and change it into products. So which means if that should happen, obviously the equilibrium would shift right. That's the language that we're going to use. So if you look at adding nitrogen, one of the reactants, what the equilibrium will try to do is consume the reactant that is added here. So the equilibrium will shift right so as to consume the added reactant, or we say the equilibrium shifts right. So the language used is always equilibrium shifts right means we get more products. Equilibrium shifts left means we get more reactants. So it's easy to explain situation rather than going about using other words. So be as short and brief and sweet as possible. That's what it is. Now, adding a reactant to product, we're going to look at the second reactant. Again, hydrogen is again a reactant, so it's going to have the same effect as adding nitrogen. Since we are adding more reactants, immediately it consumes the reactants and tries to decrease the concentration. At the same time, it increases the concentration of ammonia. Therefore, the equilibrium will shift right. Removing a reactant or product. So now if you look at this reaction again, a closed system. Now, one of the ways in Haber process, how we produce more ammonia is actually by removing ammonia, which is a product. So If you remove the product in this case, what happens? The system will try to replenish the amount of ammonia that was lost. So if that is to take place, immediately we need more of the products changing back into the reactants. I believe the explanation given, this is a difference, the same slide, I believe. Okay. The last point, if you remove ammonia, what would happen is, since the concentration is decreasing, the reactants will combine to form more of the ammonia, which was lost in the system. And in this case, the equilibrium would shift right. So every time you have a homogeneous equilibrium, it would be a good idea to look at whether you're increasing, decreasing of the reactants or products and see in which direction the equilibrium shifts. So there can be questions based on similar equations or other equations where the conditions are exactly the same. You can also explain it using concentration quotient. When we come to that, we'll talk about it. Now, effect of volume or pressure changes. Since you learned in grade 11 the pressure-volume relationship, every time the volume of a container decreases, the pressure increases, or the volume of a container increases, the pressure decreases. So we know that that relationship does exist. So whether we ask you about the change in volume or change in pressure, it's going to be the quantity of reactants and products, how they will react in terms of changing or offsetting the pressure increase or decrease that is happening. So when at least one of the reactants or products involved in a reaction is a gas, this actually is applicable. So this is a very general statement. If pressure goes up in a closed system, the equilibrium will shift in such a way so as to minimize the increase in pressure. So we said earlier, if you add something, we have to take it away. So if you add more molecules into the container, or if you decrease the volume, or if you add the quantity of the products into it, if they are reactants and products or gases, what would happen is the reaction or the reactants or products would shift in the direction so that it can minimize the pressure. Again, if you look at pressure is always force by area. Again, force is created by the number of particles colliding on the surface of the vessel. So this depends upon the number of moles. So in general, the equilibrium will always shift in the direction where there is less number of moles of either reactants or products. That's what's going to happen. So there is no specific answer. It all depends on the equation. If on the reactant side you have more moles, then it will shift in the direction which has less moles, which is forming more products. And if the products have more moles, the reaction would shift in the direction of less number of moles, which would be left. That would be the basic idea for explaining how a change in volume, which may cause a change in pressure, that will affect the equilibrium. Again, we are taking the same example because all the reactants and products are gases in this case. Now, on the reactant side, we have 4 moles. On the product side, we have 2 moles. If volume is decreased or pressure increased, equilibrium will shift in the direction of less number of moles, or equilibrium will shift right. Very straightforward answer here. Now, effect of temperature. This reaction is an exothermic reaction. Now, there are a number of ways you can look at it. One of the ways would be to consider heat as a product or a reactant. It makes it easy for our argument. If you increase the reactant, we try to consume the reactant. If you increase the product, we try to consume the product by forming reactants. So if heat is a product in this exothermic reaction, if you increase heat, the reaction is going to shift in the direction where heat energy is consumed, that is in the endothermic direction. So in the forward direction, if the reaction is exothermic, in the backward direction, it's going to be endothermic. So that's the way we're going to look at it. So it all depends on whether the reaction is an exothermic reaction or endothermic reaction. So for exothermic reactions, an increase in heat will shift the equilibrium to the left. and the opposite would be true for the endothermic reaction. So decreasing temperature for exothermic reaction, again, since the product is being removed, more of the reactants will change into products so that more heat is produced, and the equilibrium will shift right. Increasing in temperature for an endothermic reaction. So if you look at this reaction, fictitious reaction, where heat is added to the reactant to produce the products, if you increase the temperature has to be consumed, which means more and more products will form. Therefore, equilibrium will always shift right in this case. For endothermic reactions, and an increase in temperature always favors the forward direction. This decreasing of temperature for an endothermic reaction, the system will try to produce more heat, right? So what would be an ideal case? The backward reaction would be exothermic because heat would be produced. In the forward direction, heat is being consumed. So the backward reaction, the heat is being produced. Hence, the equilibrium will shift left in this case. So this can be applied to all the different reactions that you see, whether it's exothermic, endothermic, gaseous, heterogeneous, or homogeneous equilibria. Now, effect of catalyst on an equilibrium system. Is there a shift in equilibrium when we add a catalyst? We have already learned that what a catalyst does is lower the energy of activation. Therefore, the amount of energy required for the reactants to change into products is decreased. So all it does is makes the reaction takes place easily or faster by consuming less energy, but it does not affect the equilibrium position. A catalyst is a substance that increases or decreases the rate of reaction in both directions. It does not affect the equilibrium position. The value of equilibrium constant would still remain the same. So the catalyst has no effect on a reversible reaction. It only helps in achieving the equilibrium faster. The forward reaction and backward reaction will take faster, and the system of the equilibrium will achieve equilibrium. And the only thing is the time taken or the energy consumed is going to be different. But the equilibrium constant is still going to be the same. And finally, adding an inert gas. So the question is, why do we add an inert gas? So if you look at the Haber process, production of ammonia by the combination of nitrogen and hydrogen, one of the things that we do to produce more and more ammonia is we remove the ammonia produced as soon as it's formed. And then we make the equilibrium shift right. But how do we do this? We need to push the gas system from the chamber where the reaction is taking place through a compressor into a solution, which is usually something like sulfuric acid when it forms ammonium sulfate. So if this is to happen, we need a carrier gas. For that, we tend to add inert gases. Inert gases do not react with nitrogen, hydrogen, and ammonia. So it simply helps in pushing the gas out from the chamber into the container where it reacts with the next reagent, and we remove ammonia in the process and recycle the unreacted nitrogen and hydrogen along with the inert gas. So that's why we tend to add a little bit of inert gas. So the question is, by adding a little bit of an inert gas into the reaction chamber, which is supposed to be similar to a closed system, does it actually have a shift in equilibrium because of the presence of the inert gas? So if we consider a closed system where you have nitrogen, hydrogen, ammonia all in the gas phase, and along with that, if you also add an inert gas, what happens? We can calculate the total pressure. And we have learned in grade 11, Dalton's laws of partial pressures, which says that the total pressure is the sum of the partial pressures of the non-reacting gases. So if you look at that, what really happens is the partial pressures of the reactants do not change. They remain the same. And by adding this inert gas, it's not going to affect that in any way. And therefore, it does not affect the equilibrium shift. So inert gases do not have an effect on the equilibrium state. It does not make it go forward or backward. It's merely because the volume remaining constant, the partial pressures of the gases of the reactants and products do not change, it has no impact. Or we can say the concentrations ratios of the reactants and products remain the same. For that reason, inert gas has no effect in the equilibrium or shift in equilibrium. So here we have this reaction, hydrogen plus iodine reacting to give you hydrogen iodide. This reaction ideally takes place at 448 Kelvin. So normally the value for the equilibrium constant is around 50. So I just use that value. Now this is what happens. We are given values for the molar concentrations that exist in a closed system at a given time. And then when you calculated the value of Kc using this equilibrium expression, we found the value to be 40. So you have to make an interpretation as to whether the system is in equilibrium or not. And you also have to say in which direction the equilibrium will shift. So that's the expectation here. So which means there will be a part for the problem where you are expected to numerically calculate the value of equilibrium constant. And we would have given the reference equilibrium constant. You will compare it to that value and then make a prediction and a final statement. So in this case, I'm giving you the calculated value for the ratio of the product, the concentration of the products to reactants, and I found it to be 40. So the temperature at which the reaction, now the K value was determined as 448 Kelvin. The concentration ratio determined at 448 Kelvin for us gave us a value of 40, which means the system is not in equilibrium. And this number is what we refer to as the concentration quotient, because that numerical value is not the same as the equilibrium constant. So to differentiate the number that you get when you substitute it in an equilibrium expression, instead of calling it equilibrium constant, we call it concentration quotient. So you take the concentration quotient, compare it to the equilibrium constant, and make a simple prediction. And then using Le Chatelier's principle, we can actually explain it. Or we can also use the simple math ratio, the numerical values, how they affect ratios. And that's all that we'll have to do. So there are three ways of interpreting them. QC is equals to Kc. If we got a value of 50 when we did the calculation, which is the same as the equilibrium constant, we would say the system is in equilibrium. If QC is less than Kc, the system is not in equilibrium. And QC is greater than Kc, again, the system is not in equilibrium. So these are the three cases that we have. So we're looking for one of these when you solve a problem. We have already seen this. So in this case, QC is less than Kc, or QC is 40 and Kc is 50. So ideally, if you want the numerical value of 40 to go up, do we need more products or do we need more reactants? That's the question here. If QC is less than Kc, that's because you have a larger quantity of reactants in comparison to the products based on the equilibrium expression and the equilibrium constant. So you can make the number 40 go up by decreasing the numerical value of the denominator, which means reactants have to combine to form more products. So the numerator increases, the value of the numerator increases when more products are formed, and the denominator has to decrease, which means reactants are changing to products, and we would say the equilibrium would shift right. So in this case, if QC is larger than Kc, we have more products to reactants if you compare it based on the equilibrium expression, which means if you have more products here, the tendency of the reversible reaction would be to shift towards equilibrium, which means it has to come down to 60. Then more of the reactants would start changing to reactants. Therefore, the concentration or the numerator becomes smaller in time, and the value of the denominator becomes larger, which means we get more reactants. Therefore, when that happens, we would say the equilibrium would shift left if the concentration quotient is greater than equilibrium constant. So I will be posting that assignment. And then we will use those for marking it. And you'll also be having a test on Wednesday when you come back next week. Test means a quiz online based on what we have done so far until Tuesday. So just make a note of that. Now, the materials that I have here and the stuff that I make up here, and I also post it on this website over here. So if you come over here, and you should be able to see the information that I have. I try to post it on a daily basis. And study materials will appear on the right side over here. If you click that, it should give you. Now here I have actually put the outline of the content that is required from your textbook. That is from Wiley. So if you download this or click on that, it should take you to this sheet over here. I've just correlated to the topics in your textbook. So when you're reading it, you will see that these are the areas that you have in your textbook, which we will be touching, all of these areas. So you will see we have done a lot of these things already, but we'll have to go to the next part and finish it. It's not a very difficult unit. It's very, so make sure you just download this and you have an idea of what you will be doing. So this is the question that you have here. At a certain temperature, a mixture of hydrogen and iodine was used to prepare hydrogen iodide by placing 0.1 mole of hydrogen and 0.1 mole of iodine into 1 liter flask. After a period of time, the equilibrium was achieved for the reaction. When the system attained equilibrium, the concentration of I2 dropped to 0.20 moles per liter. What is the value of Kc for this reaction? So in order to solve this, we will generate what we refer to as an ice table. So this is what we call an ice table. We write the reaction in the first line, initial concentration, change in concentration, and equilibrium concentration. Some people also call it RICE. This would be R, reaction, initial concentration, change in concentration, and equilibrium concentration. So we have the reactants and products. When the reaction starts, we have 0.1 mole per liter of hydrogen. And you would notice that the information provided to you was moles and a volume. The volume was 1 liter. If you go back to the problem, you should notice that. So here, do not miss that. Here we have 1 liter is the volume of the container, and you have 0.1 mole. If this is 0.5 liters, then you know the concentration changes. So for that reason, be aware that you'll have to look at the value of the volume when you're solving these problems. So here you have 0.1 mole per liter, 0.1 mole per liter. Initially, there is 0 moles of hydrogen iodide. Change in concentration. So look at it this way. If you take hydrogen, every time 1 mole of hydrogen is consumed, it needs 1 mole of iodine. So the ratio in which hydrogen and iodine are consumed is the same, 1 to 1. At the same time, it produces twice the quantity of hydrogen iodide. So if X moles of hydrogen is consumed, it will also consume X moles of iodine. And what happens with time? The concentration of X decreases. So this negative sign over here, or minus X, indicates a decrease in concentration of hydrogen and the quantity. So minus X, and this is positive 2X. Increase in the concentration of hydrogen iodide, and the coefficient is 2, it will be twice the value. Now the problem says at equilibrium, we had this value. So the problem says we actually had 0.02 moles left when the system achieved equilibrium. That's the value that is given to you. So you can actually say that 0.1 minus X gives you 0.02. That's what you really have here. So which means the value of X is minus or 0.08. So you had to use that information that was provided to you, which stated that when the system achieved equilibrium, you really had only 0.02 moles of iodine. So using the relationship, 0.1 minus X should give you 0.02 to calculate the value of X, and then you can substitute the value of X in each of these. So here there will be a decrease in the quantity of hydrogen, that is minus 0.08. Here, there is a decrease in quantity of 0.08. That's why we got 0.02. Here, it'll be twice the amount that is formed. So once you have that, you can proceed with the calculation. Write the equilibrium constant expression. Substitute the values. Obtain the equilibrium constant. Very simple, straightforward problem. So this is one type of problem where we use ice tables to calculate the equilibrium constant. Ask you to find the concentration of any one of the reactants or products using the equilibrium constant, which will be given to you. So there are variations of problems. That's what we're really going to look at. Here is a question for you again. So the reversible reaction, CH4 plus 2O giving CO. Equilibrium concentrations. So the important aspect is we are using the word equilibrium concentration. So this value is the concentration of carbon monoxide when the system has achieved equilibrium. So the problem is pretty simple and straightforward. We are giving you the equilibrium concentrations. In the previous case, we said we have the equilibrium concentration of one of the reactants, but here we are giving you all the values. So all you do is write the equilibrium constant expression and then do the calculation, straightforward calculation here. So we will see how it goes. Again, we don't have to make an ice table because you are given the equilibrium concentration of methane, carbon monoxide, hydrogen, and the equilibrium constant is given. Kc is given as 5.67. So write the equilibrium constant expression. Again here, you should notice that the coefficient of hydrogen is 3. Therefore, H2 is raised to 3. That's the only one that you should be aware of. Substitute the numbers. The value of, again, H2O is X here. Rearrange it. And you should have the value for the molar concentration of H2O. So again, it's a straightforward, simple problem. This question, I don't have the answer. So you can take a moment, solve it, and see if you get the answer. I'm going to give you a few minutes. So if you have an answer, probably it should be 0.0668, I believe. Those of you who want to take a look at the solution, this is it. I don't have the solution on the PowerPoint, so that's the answer, 0.0668. We got that, and we have one more question. Decomposition of water at 1000 degrees Celsius has Kc value for the reaction to be 7.3 10 to the negative 18. 2H2O reversibly giving 2H2 plus O2. If 0.1 mole of initial concentration of water, what will the hydrogen concentration be at equilibrium? Now, when you read this question, a couple of things should come to your mind. We're talking about water. Water is a very stable substance. And look at the temperature for this change to take place. It's 1000 degrees Celsius. When you heat it to 1000 degrees Celsius, the Kc value is 7.3 into 10 to the power of negative 18. So a very high temperature, still water is stable, holding on to it, but a few of them actually dissociate to give you hydrogen and oxygen. That's something that should come to your mind when you read this problem. So you have 0.1 mole, which means the change in the number of moles of hydrogen and oxygen is really, really small. So see if you can come up with an answer for it. We also do make an assumption here that the actual change in concentration of water is very, very small because the number of moles of hydrogen and oxygen formed is extremely small. So if you calculate the percentage of water that is actually consumed and calculate the percentage error for the answer, we can make a valid assumption where, in most cases in equilibrium, if the answer is away by a 5% error, then it's kind of okay to make an assumption. We call it the 100th rule sometimes. So you can do that. So see if you can get an answer for this, and we'll check out the final answer. So here we have made an assumption here. So you make the ice table. We have the initial concentration 0.1. Concentration of products 0 and 0. Change in concentration minus 2x. Hydrogen is 2x and oxygen is x. At equilibrium, 0.1 minus 2x, 2x and x. So the value of Kc is given. The Kc is a very, very small number, so bear that in mind. Write the equilibrium constant expression, substitute the values. And here in the denominator, for the concentration of H2O, we take it as 0.1 minus x the whole squared. So if you consider the amount of hydrogen and oxygen that is produced, and if you divide that value by 0.1, you'll find it's a very small percentage. So for that reason, whenever the value of Kc, the equilibrium constant given to you, is smaller than 10 to the power of -3, usually you can make this assumption. That would be a safe assumption you can make. There is a method for doing the calculation. So generally speaking, if it's 10 to the power of -3 and smaller, it's safe to make this assumption. So when you make that assumption, 0.1 minus x becomes 0.1. Then your solution becomes straightforward. If not, you'll have to go to the quadratic or cube root equation. So we don't want to do that in this case because the value of Kc is very small. So when you calculate it, you should come up with a value similar to this. So the answer for the problem is 4.5 into 10 to the power of -7. If you did not get it, let me know. This is the final problem. You may want to write it down. I'm actually posting the worksheet with this questions up. Now, you may notice that in this case, we have 2 moles of hydrogen and 1 mole of iodine. Therefore, this problem will require a quadratic equation. So this is the problem that you have. Write down the numbers if you want. I'm also posting these questions up so that you can work on it. If you write the equilibrium reaction, you have it here. Molar concentrations should be calculated because here the volume of the container is 0.5 liters, and therefore you have different concentrations that are coming up here. Equilibrium expression, substitute it after making the ice stable. So this is your equation to solve for the value of x. So we will go with the 1.9 because we started with 4 moles, so we cannot have more than what we started with. Well, it would violate so many laws. And therefore, we actually have to find out the final quantity in 0.5 liters, I believe, or the actual volume. And therefore, the final answer should be in 1.9 moles. Just see if you can get that. So I will post these questions online. You can work on it. And you already had a worksheet that I gave you while you left. I think I posted it again on one of the first assignments. See if you can work on it. At this point, I expect you to be able to work on equilibrium problems, Le Chatelier's principle questions. And those are the things that we should be familiar with by this time. We have again a relationship with thermodynamics a little bit, and then we will go into solubility product, common ion effect and stuff. At this time, we have reached the 11:50, so we're going to stop the class right now. Any questions, please do get in touch with me. That's about it for now. And have a great day.